Okay, it's a great pleasure to have Clark Barwick from Edinburgh and MSRI, and he's going to talk about geometric foundations of arithmetic field theories.
Thanks, Tony. Thanks for the invitation to come speak. I'm sorry I can't be there in person, but we'll fix that some other time. So one thing I should emphasize here is the word toward, which is an important thing because I'm certainly not going to answer the question that I'm going to pose. Instead, I'm going to sort of pose it as a challenge, and I'm going to explain some other stuff that we've been doing that starts to move in this direction, but I won't meet the challenge yet. So let me remind or inform, either way, you of the idea of arithmetic topology. So this goes back to Mumford and Maser in the 1960s. And the idea behind arithmetic topology is that there's a kind of dictionary between arithmetic geometry, so the geometry of schemes that are of finite type over Z, for example, and low-dimensional topology. And so some of the elements of this dictionary are here. So for example, a number field, if you have a nice number field F, then that's supposed to sort of be an analog of a closed three-manifold. And for the purposes of this talk, I'm going to name my three-manifold MF. Now, this isn't a functor yet, but part of the goal of this is going to be to try to figure out whether or not, if there were a functor, what kinds of structure it might have. But so I'm going to pretend at the moment that there is such a functor just to tell you the ideas. So if I have a place of my number field, V, say, then corresponding to that should be an embedded submanifold. This is part of this same yoga. I'm going to denote this KV, and the reason I've chosen KV here is because in the particular case where the place is non-Archimedean, the corresponding thing is a knot sitting inside my three-manifold. So that's what happens at a non-Archimedean place. At an Archimedean place, the corresponding thing is simply a point, and that's just a point there that's part of your closed three-manifold. And then, well, what happens if I complete at my place? Then that corresponds to the deleted tubular neighborhood, KT. So I'm using the word KT or the symbol KT to suggest that it's a knotted torus, even though that's stretching the analogy a little bit. KT sub V of MF. And so the picture is something like the following. You have this nice three-manifold here. And if I take, say, a finite prime of that number field, then that picks out a knot, and then I can thicken up that knot and delete the knot, and I'm left with the deleted tubular neighborhood, which corresponds to the completion of my F at my place V. So this is the yoga, but why is this the picture? What inspired this idea? So let me sort of remind you of some kind of basic arithmetic facts that motivated this story to begin with. And the first point is, well, what if we just think about the knot itself? So why a circle, for example, at a finite place? And the point is that with finite coefficients, the Étale cohomology of spec of a finite field is the same thing as the Étale cohomology, or as the cohomology of a circle. It's exactly the same cohomology. Better still, the Étale homotopy type of spec of FQ is exactly S1, well, except with a little bit of a fudge that I need to profinitely complete these spaces, because that's just a standard sort of obstruction in algebraic geometry that I have to sort of profinitely complete things all over the place. So the Étale homotopy type of spec FQ is really the profinite completion of S1. So that means that if I take the Étale homotopy groups of spec FQ, well, then I get a Z hat in degree 1, and otherwise I get 0. And so this is the motivation for the idea that I'm going to think of this place as giving me a copy of S1 sitting inside whatever this ambient spec Z is. So let me tell you what that spec Z should look like in a minute. Okay, so that's the knot. What about the deleted tubular neighborhood of the knot? Well, to understand the reason why we'd want to think of that as a kind of surface, Here I said it was a knotted torus, but in any case, I mean that it should be a surface of some description up to homotopy. The motivation comes from here. Well, if I have a finite extension of QP, for example, then for any GE module A, I have a Tate local duality pairing. So this is a perfect pairing of finite abelian groups, where here I'm writing this a little bit strangely. So this might not be, so for the experts in the room, this might not be the way that you like it written, but I've written it a little strangely here to emphasize where the 2 is. So this is a pairing between HI and H minus I, but it's on A and something that I'm calling a dual. And this is a perfect pairing. So this exhibits this guy as the Pontryagin dual of this guy. And a dual here means Homs from A into the sheaf of all roots of unity shifted by 2. And that's the thing that I'm doing that's important here, is that I'm shifting this thing by 2. And so this 2 is reflective of the fact that you have a 2-dimensional duality theory here.
Sorry, Clark.
Yeah.
G is Galois group?
Yeah, G is the absolute Galois group of E. That's right.
And so this is some kind of a Tate duality that you're writing?
Yeah, this is Tate local duality. That's right.
Yeah, but isn't there a Tate twist somewhere?
Yeah, the Tate twist is bunched into this mu here.
Oh, okay.
This is the roots of the sheaf of roots of unity. Yeah, that's right. Yeah, so this 2-dimensional duality, this 2 is this 2, is sort of inspiring us to think that this KTV, this thing, should actually be a 2-dimensional object, a surface. And indeed, this has kind of inspired a whole kind of enterprise of things. So for example, one particularly exciting recent development has been that this picture has been geometrized to some extent using what's called the Farg-Fontaine curve, which is a literal curve whose cohomology is reproducing for us this cohomology. So I'll talk about that in a minute. Okay, so that's the story of the non-Archimedean places and this completion of those non-Archimedean places. But what's motivating the idea that this thing should be a 3-manifold? Where does that come from? So that comes from a global form of the same duality. So here's the statement. If I start off with a constructible sheaf F on spec OF, so this is a constructible sheaf for the Untitled topology. And now I need to hedge a little bit here. And the way in which I'm going to hedge is I'm going to assume that either F is purely imaginary or that F has no 2 to the n torsion. I'm going to address this hedging in a little bit, but let me just leave that here like this for now. Then there's a global duality theorem. And the global duality theorem is again a perfect pairing. And the perfect pairing takes the compactly supported cohomology. I'll say what compact support means in a second. And it pairs it with H minus I of something that I'm calling F dual. And once again, that's a perfect pairing into Q mod Z. So this exhibits these things as the Pontryagin duals of each other. And here F dual is Homs from F into GM shifted by 3. One of the funny points here, let me just emphasize, is that this is again a constructible sheaf, even though GM shifted by 3 is not in any sense a constructible sheaf.
By the way, when you say
constructible,
what's the stratification you're taking? Is it just close point, open point, or?
No. So I'm allowing for an arbitrary finite constructible stratification.
Oh, okay.
So it's constructible relative to a finite constructible stratification on the scheme. That's right. Right. So there's this compact support business here, and the compact support has to do with the fact that we're really going to take spec OF and we're going to compactify it, and we're going to compactify it by adding in the Archimedean places. And to do that, what we do is we essentially add just a single geometric point for every Archimedean place. And how do we add it on? Well, in order for me to add a point onto an open manifold or object, I need to tell you what its deleted tubular neighborhood is. And the traditional way of doing that is to add it so that the deleted tubular neighborhood is the classifying space of the completion. So in the same way that the Attall homotopy type of of, say, a spec of a local field is really nothing more than the classifying space of the Galois group, we're going to do the same thing for the Archimedean places. And we're going to simply choose this to be our deleted tubular neighborhood. So I'm going to come back to this point because I want to modify this in some sense to get a slightly better theorem out of this, but that's going to be toward the end of this talk. In any case, what's the point here? The point is that I have something akin to a three-dimensional duality. I have this funny sheaf that I've gotten, which is acting like a dualizing object, but it lives entirely in degree 3. And so that means that this is really functioning now as a kind of three-dimensional duality pairing. So that inspires me to think of this thing as some sort of three-dimensional object that I'm then compactifying by adding in these Archimedean places with these closed points out at infinity. Okay, so that's the story. That's roughly the motivation for the idea of arithmetic topology. And this story is sort of kind of existed in various forms and been talked about in various places for a number of years. And one of the things that I'm going to try and describe today is I'm going to describe a program to build off on that picture, that arithmetic duality picture, to really start to understand things like field theories on these things. But before I do that, let me just, I thought I'd include a kind of cute example, sort of some concrete way to visualize what's happening here. And the concrete example that I'm going to write down here is probably one that's familiar to everyone. But if you take the 2 primes that are congruent to 1 modulo 4, well, these 2 primes correspond to certain knots sitting inside my 3-manifold. Let's inspect Z, right, which I'm regarding as a 3-manifold. And I'm certainly allowed to speak of the linking number between 2 things. That's an entirely homotopical construction. Basically, you cut out one of the knots, you look at a double cover of what's left over, and then you look to see whether the lift of the previous knot lifted into 2 pieces or 1 piece. You just count the connected components. And this is giving you, well, not quite the linking number, but a sort of mod 2 linking number. So this mod 2 linking number, we can think of that as either a +1 or a -1. And this turns out to coincide precisely with the Legendre symbol. So in other words, this is sort of homotopical construction. It's just doing pure homotopy theory with these Étale homotopy types. But when you really think about this construction, you're actually reproducing the Legendre symbol. You can push this further. You can talk about higher linking numbers by talking about Massey products, again, sort of in a purely homotopical fashion. And these turn out to coincide, or at least a triple linking number turns out to coincide with a Radii symbol. So I learned this from the thesis of Vogel. And so you could do something kind of funny. You can start to look for examples of Borromean primes, situations where the 3 of them are linked, but no 2 of them are linked. And this is all happening mod 2. And it turns out that I actually know an example of these, which is 13, 61, and 937. It's thought that there should be infinitely many of these. I sort of have a probabilistic argument for that. And actually, Vogel actually produces an algorithm for computing them, which is a little complicated, but you can actually sit down and extract these things. So I think in the first, I don't know, 10,000 of these triples, you see about 25 of these Borromean triples. And I think this is the smallest one. Anyway, I just wanted to emphasize the fact that you really can do something extremely concrete with this picture. I mean, you can really kind of get your hands dirty and understand these objects in a very concrete way. And so this is the story of, yeah.
Concerning the computing these triple. So this can be congruences given by congruences or by something, quadratic congruences, or what? How do they help? Yes.
Are you asking how do you compute the Radii symbol?
Yes, yes.
Yeah, so the rough idea is the following. So I'm not going to get this exactly right, for which I apologize. But the rough idea is the following: that you take two of these primes. These correspond to 2 different knots, and then you look for quaternionic covers of the complement of those 2 knots.
Mm-hmm.
And then you look at what becomes of the 3rd prime in your group.
So it's not simply congruences, linear congruences, but it's something more common.
No, it's not simply linear congruences. That's right.
Okay, thank you.
Yeah. Yeah, by the way, I mean, if you're interested in these radii symbols, I mean, I really strongly recommend looking at these papers of Vogel. They're really beautiful. There's a whole story there that I was embarrassed that I was so ignorant of. It's really fun.
There's some papers of Sharifi also that are quite cool.
Oh yeah, Sharifi.
Sharifi, yeah, he's been working on Iwasawa theoretic versions of these things.
Am I spelling that right, Ted?
Sharifi, yes. Romeo Sharifi, yeah.
That's grand, thank you. Okay, so how do we make this story precise? That's the first question. And I sort of have indicated how you might go about this is I've been talking a lot about the Untitled homotopy type. And so I'm going to get into that in a minute. But let me first, actually, before I talk about the Untitled homotopy type in more detail, I want to mention that that there's this idea of Min-Young Kim, which is to take this arithmetic topology as a platform from which you can build the idea of field theories. So the idea here is that Kim predicts that if we understood arithmetic field theories, that is to say field theories defined on these interesting small dimensional manifolds, that these would organize a lot of the difficult things that we're after when we try and do number theory. So for example, the Fukaya-Kato conjectures on L functions should be easily, or quote unquote, easily extracted from the right form of field theory on this MF. So more precisely, the Fukaya-Kato conjectures predict the following thing. They predict that if you look at the moduli space of constructible sheaves, so these are sheaves on MF, if you look at the moduli space of constructible sheaves, then if you look at the determinant bundle over it, then the L function should essentially be reconstructible from a kind of amplitude on that. There's a certain section of that determinant bundle. And the question is, can you construct that with all the properties that they predict? And there's a large number of properties that they predict. And the conjecture is that if you really understood how to write down field theories, then these things would sort of exist as amplitudes for your corresponding field theory. They'd actually be honest amplitudes for your field theory. So this leads to the motto that L functions are the same things as wave functions. Perhaps more speculatively, or at least for me more speculatively, just because I don't understand these details yet, the same role that's played by conformal field theories in geometric Langlands might be portable to the context of local Langlands because of this sort of new geometrization that is happening in the work of Schulze and Farg. So in any case, so the question is, what do we do with this idea? And I think there's sort of two options for what you can do with this idea. One idea is to simply just take the idea of an arithmetic field theory as a conjecture generator. So this is very much what I think is common in what David Ben-Zvi is doing right now. And well, yeah, David Ben-Zvi is the most obvious example of someone doing this right now. And you don't worry about what one actually means by any of these arithmetic field theories. You simply use them to generate more interesting conjectures. Another approach would be to at least try to define some of the salient structures of these field theories. So for example, one could try to make sense of the observables of such a theory. And maybe if we just understood that, we would already have some kind of insight into how to construct these things for real. So then what's the goal? My goal would be to try to construct interesting examples of factorization algebras on this mythical three-manifold MF. And so that brings up the following challenge, which is, well, what exactly is the Ron space of this thing? Can we describe the Ron space of MF in a way that's good enough to try and understand its category of constructible co-sheaves, and therefore of its factorizable co-sheaves? And so then that would be a natural place to start looking for the observables for various kinds of field theories. Okay, so how could we possibly go about this? And I think, a reasonable starting place is to really understand what kind of object this MF is. And so now let's go back to this discussion of the Étale homotopy type. So this is in some sense going to be the 0th approximation to my MF, and you'll see why I say 0 in a minute. So the Étale homotopy type is a profinite homotopy type. And it's defined in the following way. Well, I'll give you actually a very precise definition in a minute, but it's defined at this level of specificity. It's defined so that its pi naught is the sort of Étale components of X. Pi 1 is the Étale fundamental group of X. And its cohomology with coefficients in, say, some finite local system is the same thing as the Étale cohomology with coefficients in a corresponding finite local system. So it's exactly set up to reflect all of these properties. So let me write down some examples because it's fun. One example, well, if I just take spec of a field, then the corresponding Étale homotopy type is the classifying space of the absolute Galois group of my field. Nothing really happened there. Well, now if I have a scheme of finite type over the complex numbers, then I can take the complex points of that scheme, and if I think of those things as sort of glued together from things that sit inside CNs of various sorts, then I get an induced topology on those things. And with that classical topology, I have an associated homotopy type. And I can profinitely complete that homotopy type. And when I do, I actually recover the Étale homotopy type of X. Oops. Well, one thing that we decided was going to be very interesting was if I tried to understand the Étale homotopy type of spec Z. Unfortunately, it's not interesting at all. It turns out it's just a point. This is, at the level of pi 1, this is the fact that Q doesn't have any non-trivial unramified extensions. Things are a little more interesting if you're willing to involve something like the Gaussian integers. This turns out to be the cofiber of the degree 4 map from S2 to S2. And that's the Étale homotopy type of the Gaussian integers. So you might be a little unsatisfied with this. Part of the motivation here is supposed to be that, well, this thing is just really an open 3-manifold and it happens to be contractible. So we're supposed to be thinking of this as kind of an R3, and then I'm going to sort of compactify that thing somehow. But there are issues already with this story. And let me just say 2 of the issues right now. The first one is that really this Étale homotopy type can't see the structures that we've said that we wanted to study. We said that inside our MF, we wanted to see knots and we wanted to see deleted tubular neighborhoods of knots. So we'd want to be able to see things like embedded submanifolds and their deleted tubular neighborhoods. And we don't have access to that stuff with just a raw homotopy type like pi infinity at. Another issue that arises is that, well, we were interested in global duality, and global duality was really a statement about constructible sheaves. But this pi infinity et here can only see local systems. And that's why, for example, this global duality, which is supposed to be showing us all this interesting 3-dimensional behavior, pi infinity et can't see any of it, right? It's just contractible. So in order to fix this, in order to really see the kind of phenomena that we're interested in with the global duality, we need to find a version of the homotopy type that's capable of seeing constructible sheaves, not just local systems. And so that leads us to our first approximation to this object MF. And that's what I call the stratified Étale homotopy type, which I just denote by gal X. So the moral of the story is going to be that gal X knows about constructible sheaves in the same way that the Étale homotopy type knows about local systems. So the relationship between the Attall homotopy type in local systems is called the monodromy equivalence. And so correspondingly, what we called the relationship between gal X and constructible sheaves is what we call the exodromy equivalence. And I'll show you what's so exo about this story in a moment. So, but first I want to tell you a theorem. This is a theorem of my graduate student who's actually finishing this year. My graduate student, Peter Hain, proved, in a sense, the kind of fundamental fact that we need to be able to use in order to tell this story. And that fundamental fact is the following. Well, if you think about classical homotopy theory, there's this equivalence between homotopy types and infinity groupoids. So one way to think of this is that this is the relationship between homotopy types regarded as topological spaces, say CW complexes. And these are simplicial sets that satisfy the Kahn condition. And what Hain proved is that this equivalence between homotopy types and infinity groupoids extends to an equivalence of homotopy theories between stratified homotopy types and infinity categories with the property that every endomorphism is an equivalence. So I think the way Peter calls these layered infinity categories, if I remember right.
Sorry, is a stratified homotopy type just the exit path category of a stratified space, or is it something more?
It's something more intrinsic. So the functor here is the formation of the exit path infinity category of the space. But the stratified homotopy type is a stratified space, first of all, is a topological space, along with a continuous map down to a poset where you give the poset the Alexandrov topology. So I'm allowing myself arbitrary posets here. And the point is that this category, the category of these things, can be given a homotopy theory. You can say what you mean by weak equivalence. And what you mean by weak equivalence is that you want to have a weak equivalence on strata and links. And that's a good theory, provided that your X is nice enough. So let me not say what nice enough means right now, unless you insist.
Nice is a condition of the stratification.
Nice is a condition on X with its stratification. That's right. And it's a relatively complicated condition to check in practice.
Right, something conical and
conical would do the job. Yeah. Yeah. If you have a conical stratification, that's nice enough for my purposes. To do more than that would probably be, I can be more general, but I don't want to be. But the point is that if you take the category of these things along with that class of weak equivalences stratum-wise and link-wise, then that gives you a homotopy theory. And that homotopy theory is equivalent to the homotopy theory of infinity categories in which all endomorphisms are equivalences. So the fact that this side embeds fully faithfully into this side was a theorem of Ayala Francis Rosenblum. And they conjectured that in fact it was an equivalence, and that's exactly what Peter proved as one component of its thesis. Okay, so what is this giving me permission to do? Well, it's giving me permission to think about stratified homotopy types entirely in these abstract terms. And the reason that that makes me happy is that's exactly what we got to do with the Attall homotopy type. In Artin and Mazur, it's an absolutely critical component of their story that they're allowed to think of homotopy types as simplicial sets. And that allowed them to work very algebraically with those objects. And we want to have the same ability because we want to think about the stratified homotopy type attached to a scheme. And so really what we want to do is we want permission to just think about infinity categories in which all endomorphisms are equivalences. So by the way, let me just comment that for those of you who don't like this symbol infinity in front of words, I'm going to make things a lot better in a second here, and I'm actually going to get rid of the infinity. It turns out that in a certain limit, the infinity just disappears. So in fact, the stratified homotopy type attached to a scheme is actually just a one category. It's not an infinity category at all. Now, once again, because we're doing algebraic geometry, we have to say profinite everywhere in the same way that the Attall homotopy group is a profinite group. But nevertheless, we can say precisely what this category is in very concrete terms. So an object, so this is going to be a category that I'm writing down. So an object of this category is going to be a geometric point, x of x. And this geometric point, when I say geometric point, what I mean is that omega is a separable closure of the residue field of the image. So that's what an object will be. And then I'll have to tell you what a morphism will be. And a morphism from a geometric point x to a geometric point y is a specialization that goes in the other direction. Or maybe I'm supposed to say generalization here. So what precisely do I mean here? Well, I mean that if I've got this geometric point x and this geometric point y, then I can take the strict localization of x at little x. And then the data of this map is the same as the data of a lift of y to a geometric point of this strict localization. So in this particular case, if I look at the image points in the Zariski topological space of x, in this case, I'll see that the image of x is contained in the closure of the image of y. So it's a specialization at the Zariski level, but this is extra data now on top of that. And that's what we're keeping track of in this category. So this is really the category. This is the category Gal. And this is the category that we study in the book that we just put out on exodromy. And so the claim is that you can actually compute this thing up to the fact that you don't know what any absolute Galois groups are. You can compute this thing in a lot of interesting examples. So let me write down a few of these now. Well, first I have to do the conventional example. I have to take a field and I have to look at Gal of it. And I have to see that, well, a point of this, an object of this category, is the same thing as a separable closure of K, and a morphism is just an isomorphism between these two separable closures. So I'm ending up with just a copy of the classifying space of the absolute Galois group of K. So once again, nothing much happens if you just take a field. But things are a lot more interesting if I take a DVR. So if I take a DVR, A, with residue field little k and fraction field big K, then this Galois category is actually a lot more interesting. So up to isomorphism, it has two objects, this one and this one. This is the closed point and this is the open point of my DVR. The automorphisms of the closed point are given by the absolute Galois group of little k, and the automorphisms of the big point are given by the absolute Galois group of big K. But then I have to answer the question of what the morphisms going in this direction are. There are only morphisms in this direction because this is contained in the closure of this. So there's only morphisms going this way. But what are they? How can we write them down? So suppose that I chose a particular model for this point and a particular model for this point, right? So that's choosing a separable closure of little k and a separable closure of big K. Then the space of maps from here to here is actually given to you by the fiber of the map from the classifying space of the decomposition group to the product of these two classifying spaces, BG little k and BG big K. So here, remember, the decomposition group sits inside GK. Normally, it's only defined up to conjugacy, but this map from the classifying spaces is uniquely defined because I've gotten rid of the base points by passing up to B. And remember, this map here is the quotient map. This is the usual map that says the decomposition group mod the inertia group is the absolute Galois group of little k. And so what's the picture here? The picture is that, well, I have this kind of bulk, which is the classifying space of the Galois group of big K. And that's the complement to this thing here, BG little k, this circle here, if you like. I've just drawn it as a circle because I'm constantly thinking of the finite field as the closed point, but I could be more general. And then the deleted tubular neighborhood of this closed thing is this green area here, which is the classifying space of the decomposition group. And that's the picture in the case where A is a DVR. But as soon as you've understood the picture in the case where A is a DVR, you can imagine doing the same thing for spec of Z. You just repeat this same story at every single prime. And you keep track of the fact that because the topology is profinite, you can only see finitely many primes. You can only keep finitely many of them in focus at any time. So you see the same picture replicated again and again and again for the knots inside spec Z.
Clark, may I ask something?
Yeah, of course.
In the case K, suppose that K is the completion. Yes, it's a complete DVR.
Yeah.
Yes. Then what are the morphisms? It's simply all the sections up to conjugate. I just want to understand.
So the morphism, so you're saying in the case where K is a complete DVR, yes?
Yeah. So then you know that actually, so the G little k is the quotient of GK by the inertia group. So but I was wondering, what are these simply complements of that? What is the
complements? I mean, it's really just the fiber of this map. It's really just, so I mean, maybe another way of saying it that you'll like better is that I'm looking at the set of sections of, so there's a functor.
Yes.
From this category to say this poset. It's kind of boring.
Mm-hmm.
And I'm looking at the set in the set, and what I claim is that if you look at the space of sections of this, then that's the classifying space of the decomposition group, and that's always true.
Okay.
For any DVR. So it's another way of kind of breaking up the space. So the set of maps, you don't have to worry so much about the set of maps because it's really more important to understand the space of sections, as it turns out. I wrote this down to be friendly and concrete, but the space of sections is the thing that really has arithmetic relevance, and that's the decomposition group or its classifying space.
So the way you defined it, the morphism between the close point and the general point, they don't compose at all. The composition only happens in endomorphisms, and you can compose endomorphisms with morphisms.
Yeah, you can compose morphisms with endomorphisms with morphisms. That's right.
The DA guys, even though there is a composition there, you're ignoring it. That's.
Well, it's the classifying space of the decomposition group. Right. So the morphism space, right, is connected. There's only one map up to equivalence.
I see.
but that map has maps.
Yeah. Well, and I think that maybe you also did not explain us, but on the previous slide, the morphism, if you take a point and then the closure, yes, with this. Is it here? Yes, yes.
Yeah.
So this is not so, okay, specialization, but now this involves then all this machinery, which you explain later now, in order to define the morphism.
Well, I mean, so this is a correct definition of the morphisms. This is the whole thing. There's nothing more. I haven't swept anything under the rug at this stage. This really is the set of morphisms from here to here. Is that what you're asking me?
Yes, yes. So almost. Yes.
So it's really literally just a lift of this geometric point. So this is spec of some. This is spec of some separably closed field. Yeah.
Yeah. Yes. So, yeah.
Omega prime.
So that was my point. So the point is that if X is in the closure of Y, then you must find somehow a canonical map from the closure, algebraic closure of, so the Galois group of X and Galois group of Y. Yes. So in order to have the.
Yeah, that's right. The data of a map is all of this structure. It's not just simply that this guarantees you a map. You know, this guarantees that X is contained in the closure of Y, but over such a pair of points, there are going to be many, 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 many maps, right? As we see in this example here.
Yeah, so that was.
Yeah, there are many, many maps just because at the Zariski level, you might have a specialization, but I'm saying a specialization of geometric points should be defined in this more general way.
Okay.
This is maybe the right thing to say is something like a tall specializations. Maybe that would be a more correct way to say this.
So in your diagram on the top where you're describing the category, you should
Yeah.
have B's everywhere, right? You should have BGK for the...
Well, I guess it depends on your attitude about what I've marked here. So here, I mean, the set of endomorphisms of this object is exactly GK. And here, the set of endomorphisms of this really is GK. And here it really is, I think I said something a little quickly before, and I think I might have ended up misspeaking. So what I should have said was the following, that the set of maps from here to here, it's the fiber of this map. It's the set of,
Okay.
So this fiber is a space. It's a set though. It actually turns out to just be a set up to homotopy.
Mm-hmm.
Because DA embeds into here. So, yeah, exactly. DA is a subgroup of GK. So, exactly. Yeah. Yeah. So this is a fun example. Oh, and I'm going to give another example real quick, which is the following, which is that well, remember we had this thing where if you took the Étale homotopy type of something over the complex numbers, then in effect, you could take the classical topology on the complex numbers and recover that Étale homotopy type. So you could ask, is the same thing true here? And the answer is yes, absolutely. And so here's that statement. So if you have a scheme of finite type over the complex numbers, well, you can take the complex points, again, with its classical topology. So you should think of this as a complex manifold. And well, what happens? So for every algebraic stratification of that manifold, I'll get a corresponding stratified homotopy type. I'm going to take the limit of all those stratified homotopy types over all the possible algebraic stratifications. So I think of that as the stratified homotopy type relative to X zar, not just a fixed finite stratification, but over the whole Zariski topological space. And then once again, I have to profinitely complete. But once I've done that, you actually recover this gal X in all cases. So this is sort of this is a stratified Riemann existence theorem. And this is proved in the exodromy book. Okay. So here's the picture that we have now of gal Z, and you'll notice that I just literally copied and pasted this picture from the other page, because now we really have this in a strong sense. We now know what it means to have a homotopy type that has the ability to have things embedded inside it, like this knot here. This really is a knot embedded in some larger homotopy type, and we really can speak about its deleted tubular neighborhood. And that's given by the decomposition group, or equivalently, the classifying space of the absolute Galois group of QP. And so now we really have the picture that we were modeling earlier. And so this really is a good approximation to our expectation, our expected MF, that is to say, when F is Q. Okay, so let me tell you 3 theorems that we proved about this stratified homotopy type. And this will indicate to you why it is that I wanted to use precisely this stratified homotopy type to start thinking about this MF. And the first theorem is the exodromy theorem. That says that in the same way that if I took local systems of X with any sort of coefficients that I like, then I can think of those things as continuous functors from the Étale infinity groupoid of X valued in that same category. Here I can take constructible sheaves on X valued in anything. Here I wrote perf lambda to emphasize that that's the kind of thing that I'm mostly going to be interested in. And these are the same things as continuous functors from gal X to perf lambda. So what's the functor here? Well, if I have a constructible sheaf on X valued in perfect lambda modules, then for any geometric point, I can take its stalk. Right? And that's actually functorial in the Galois category. And so that actually defines for me a continuous functor here. And so that's telling you what the functor is going in this direction. And the theorem is that this is actually an equivalence of categories. So this is the sense in which constructible sheaves really just form a functor category. I have to say continuous. So there's a little funny business here. Here I'm using the fact that I have a profinite topology here. And for example, in the case where lambda is something like QL, I'll need to use a topology on perf. So to do that, you need some piece of the pycnotic or condensed formalism. But that's the exogyny sentence. The homotopy sentence is the sentence that the Étale homotopy type, the thing that we were starting off by studying, can be recovered from Gal simply by taking the nerve of that category. And if we take the nerve of that category, we end up with some sort of space, and that space turns out to be exactly the Étale homotopy type of X. So this is kind of interesting because, of course, the Étale homotopy type of X is in general quite a complicated thing. So for example, if I take P1 over the complex numbers, you know, that has lots and lots of homotopy groups. But this is really just a one category. Gal X is just a one category, but its nerve is actually recovering somehow abstractly all those homotopy groups. And then third and lastly is the Reconstruction theorem, which says the following: if I take a normal variety X over Q, I've said Q here, but I should really emphasize that any finitely generated field of characteristic 0 is good. Finitely generated over Q as a field. If I take a normal variety over Q, then Gal X is actually a complete invariant. It's complete in the following sense: there's a fully faithful functor. The assignment of X to Gal X is a fully faithful functor from these normal varieties over Q to profinite stratified spaces over BGQ. And the maps that I have to use, however, have to send closed points to closed points, or sort of closed subsets to closed subsets.
So how is this related? So there is this recent reconstruction theorem of Kolar, Lieblich, Olsen, and Salin.
Yeah.
That says that for dimension 2 or higher, you can reconstruct from the Zariski topological space. But they require normal. You don't have any condition. Oh, sorry, they require proper and normal.
Yeah, that's right.
You don't have any proper.
That's right. I don't know the connection. So I mean, in their case, they're also focused mostly on things over the complex numbers or over an algebraically closed field. So I don't have a very good story to tell you about this yet. But my sense is that their story is very much a kind of it's very much like this sort of the Bogomolov-Anabelian conjecture. You know, this approach where you're trying to work over an algebraically closed field everywhere, and you only get sort of birational equivalences and things. And this is really closer to a sort of a stratified form of the Anabelian conjecture itself, because we're working over these kinds of these lower bases, these fields of these finitely generated fields. But I don't have a better story than that to tell you right now.
Sorry, in the second part of the session, isomorphic to map. So you said that actually here you require that close points should be mapped to close points. Yes.
Yeah, that's right. That's exactly right. Yeah.
I was going to ask about the reference. Is this all in the book?
Yeah, this is all in the book. Yeah, this is an exogyny. All three of these sentences are in the book. Yeah, absolutely. Absolutely. Yeah. By the way, I mean, for those of you who like this sort of thing, I mean, I would expect that something like this should be true also over finitely generated fields of characteristic P, but I don't have a proof. I don't have a proof. There could be some funny business there, but it seems like it should work.
Yeah, so maybe in characteristic P, maybe you have to take care of what is it, two inseparable covers, which do not see points.
Right, that's right. So what I mean by this is that you need to invert universal homeomorphisms.
Yes.
Right. Yeah, that's right. So on this side, you'll have inverting universal homeomorphisms, and then this should be an equivalence again. So in other words, so in other words, you know, you could take perfect varieties. They're not a finite type anymore, but you can live with that. So you'll take perfect varieties. So you'll take the inverse limit along all the Frobeniuses and you'll get something that's gigantic, but it sort of is topologically a finite type, if you like. And then those things should be equivalent to these things. Yeah. Yeah, I mean, I think all of that should be possible. I haven't proved anything like that. Okay, so these are the three theorems. These are the theorems, and in particular, this first one is really strongly suggestive of the idea that this is the appropriate place. If I take X to be spec Z, then this is really reconstructing my category of constructible sheaves. So perhaps this is the right place to sort of see the structures that I'm looking for in MF. But I'm still missing a piece, which is that in this story MF, I'm supposed to have a compact 3-manifold. So the question is, what became of this compactification that we said we were going to do? So we said that we were going to add, for every Archimedean place V, we were going to add a new point. And the traditional way of adding that point is to take the deleted tubular neighborhood to be BG of the completion of F at that place. But I want to argue that at real places, this is perhaps not such a great idea. And so to do that, let me emphasize the following. Well, when you perform this construction, this is your point at infinity corresponding to the Archimedean place of Z. This is the Galois group, and it's going to be a big open inside our compactification. And then this is the thing along which you're gluing. And this is going to be a homotopy pushout. But if I do this for my homotopy pushout, well, then I'm taking the classifying space of GR, and so I'm getting RP infinity up to homotopy. Here I just have a point, and then over here I also just have a point. So if I form this homotopy pushout, I'm going to be left with the suspension of RP infinity. And the reason that I'm a little unhappy right now is that this is not in any sense a 3-manifold. It doesn't have cohomological dimension 3. It doesn't have any of the structures that you want. The problem is, of course, all with 2 torsion coefficients. It's sort of located in that area. So that's the reason why in the original statement of global duality that I gave, I was avoiding the 2 torsion coefficients in this story. Because of course, the 2 torsion cohomology of this is not so finite dimensional. So how could we fix this? And the idea actually is an idea that's sort of quite trendy these days, this idea of the Farg-Fontaine curve, but at the infinite place. And the idea is that the absolute Galois group of R, or its classifying space, is really a shadow of a more sophisticated object, which is the twister line. This twister line is, well, if you take, I guess the way to say this is that you could say that it's the Brouwer-Savary variety over R of the quaternions. Or equivalently, you could take P1 over C, and you could look at the map that carries Z to -1 over the complex conjugate of Z, and use that as your descent data down to a real variety, and you'll extract this guy. So this is the twister line, and this twister line has some really remarkable properties, but perhaps one of the most remarkable properties is that if you look at suitably equivariant vector bundles over the twister line, then that reconstructs for you the category of real Hodge structures. So this twister line is quite a nice object, and its Étale homotopy type is actually an RP2. And this RP2, its fundamental group is, of course, GR again. But of course, there's a lot more homotopy happening in this RP2. So you could just sit down if you wanted to and replace BGR in the pushout that we saw on the previous page with the Étale homotopy type of the twister line. If you do that, well, then here we have RP2. And once again, we have point and point. And when we form our homotopy pushout, we're going to end up with the suspension of RP2. which is, it's certainly not an oriented three manifold in any sense, but it does have cohomological dimension 3. And so for that reason, it would be, I would propose that this is the correct Étale homotopy type of the compactification of gal of Z. So this is now starting to look a lot more promising. This is a lot closer to our MF object. I will mention sort of parenthetically that it would be a good idea to replace everywhere, actually, the Galois groups that appear with their corresponding Weil groups. I don't actually know how to do that systematically. And that has to do with the fact that I don't really understand the Weil group of global fields very well. For local fields, I think I've got it, but for global fields, I'm very confused. And I mean, even further, it could be the case that there's a suitable homotopy type of the Farg-Fontaine curve that isn't just a k-pi1 that should probably be glued in as the deleted tubular neighborhood. But I'm going to leave that as a kind of speculative parenthetical remark. The point of this is the following theorem. And this is, in a sense, the final actual theorem that I'm going to state. So if you have a constructible sheaf, now not on gal OF, but on this compactification that we've written down, then we in fact have a perfect pairing. So again, this is an instance of Pontryagin duality. And what are the two groups? Well, I'm taking the cohomology. Now this is of this compactified guy with coefficients in F. And here I've got the cohomology of the dual in negative degrees. And it's a pairing, and I've written this pairing as to land in actually the circle, not just Q mod Z anymore. And this turns out to be necessary. But the main point here is that the dual is R hom from F into GM shifted by 3. And so there's our three-dimensional duality. But the key point here is that nowhere have I used the fact that I have any assumptions on F. F is no longer necessarily purely imaginary. And my script F here doesn't have to avoid the prime 2 in its torsion. This is just simply a true sentence without any kind of funny business. Okay, so the upshot here is that this is, yeah.
The bar in the Archimedean places, you did insert the twistor line, not the...
Yeah, I'm inserting the twistor line at both the real and the complex places. That's right. So I'm getting, so I'm gluing on these RP2s and S2s at the infinite places. Or rather, those are the deleted tubular neighborhoods of the things that I have at the infinite places. Yeah, so I'm adding those things on by hand. And when I do, it resolves this issue with the prime 2. Exactly does that. Which in the case of Z, I mean, you can kind of see that just by hand. In more general cases, I should emphasize that I'm not avoiding the use of global duality in proving this. This isn't a new proof of global duality. I'm still using the old technology. I'm still using all of class field theory to write something like this down. But the point is that I'm avoiding some of this sort of, some of this kind of the problems at the boundary of the theory. So my upshot is that this is this compactification is a reasonable approximation to our MF. It's not got everything that we could hope for, but it's a reasonable approximation in the sense that it is a stratified homotopy type that seems to be naturally associated to this MF. But from the point of view of the challenge that I mentioned, I haven't gotten very far. So this is where the talk is going to stop. I wanted to try and construct the stratified homotopy type of a Riemann space attached to MF. What I'm proposing here is that I've constructed something like the stratified homotopy type of MF itself, or at least an approximation there too. But somehow there's some extra information here. We have access to geometrizations of certain pieces of that stratified homotopy type. So for example, the closed strata have concrete S1s that are sitting inside them. And these deleted tubular neighborhoods have the Farg-Fontaine curve sitting inside them. And so you could give something like a provisional definition of something like the Riemann space of the Farg-Fontaine curve. Well, it would be very interesting to use this. Again, this is just sort of in the speculative realm. It would be very interesting to use this to try to construct something like conformal field theories on the Farg-Fontaine curve. But that's all speculation, so I think I'll stop now.
Thank you, Clark. So questions, comments?
Maybe I have a, okay, so. Hi, Clark. Once upon a time.
Hey there, how are you?
I don't, what did you TA? I think the number theory? And I don't, or algebraic geometry. Anyway.
I can't remember.
So, I wonder, so the point is that the so-called twisted line, yeah, so the very brown, that makes sense also over the local fields. Why you do not, you avoid it there, why use it over the complex numbers or over the infinite places? It's just, what is the deeper meaning, or is?
I don't think there's a deeper meaning. I think it's just laziness on my part. I think what it comes down to at the moment is that I don't understand enough. I mean, so for example, you mean that why I haven't included something more elaborate like the Farg-Fontaine curve?
Yes.
So the simple answer is the following. So if you look at the Étale homotopy type of the Farg-Fontaine curve, the ordinary Étale homotopy type, nothing particularly fancy, then you end up with exactly the Étale homotopy type of QP.
Yes.
It's just BGQP. That's true at the fundamental group, but it's also true for all the higher guys. So there's no benefit to adding the Farg-Fontaine curve from the point of view of the homotopy type of this MF. You don't get anything new. Whereas you do get something new by passing to the twister line.
Yes, that was my question. So I actually, somehow when I heard this story with the Farg-Fontaine, actually people doing Galois theorems, I knew these things already in the 80s. But because somehow they were not in the realm of, I don't know, the new theories, okay, so what? Yeah. But I think that the twisters somehow, that has to do something. And then after that, concerning why not the twister over the twister and so on, I think that these iterative constructions have something which are very specific, which is very specific for them. Yeah. Anyway, just was.
So say it again, the iterative constructions have.
So the point is that actually the twister, the twister line, how you call it.
Yeah.
So that makes sense over any variety.
Yes.
Yes. And my question is maybe this might be something very, very, how should I call it? This might hide something very interesting.
Oh, I see.
Yeah.
Do we know anything about the vector bundles on the twister line over another variety?
Well, it's to be honest, I never thought very deeply about this, but I think that it's related to the two-torsion cohomology, yes, of the variety.
Ah, okay.
And now the whole point is now it starts the cohomology. So the cohomology that in general the two-torsion and so on is different than the so-called Brauer variety. So the two-torsion and the Brauer group, and there is a discrepancy depending on how good the variety is. Yes. I mean,
good in the sense of smoothness, or in the sense of?
Yeah. So the point is actually, if it is smooth, then actually all the two. That is one thing, and the second thing is also, I think that in the Z-mod two torsion, then you have, it's also that yes, you have the Brauer component, but the true Brauer component, but you also have something with the it encodes something about the two torsion in the fundamental group. Yeah, that is my so that is all for curves, for everything over local fields, over fields in general. I think that somehow I have the feeling that the twister line is something which is much deeper than this playing around with I don't know what kind of completions. Anyway, so.
Ah, I see. Okay, that's thanks. I should think more about this. I've I've really only thought about it in these two cases of over R and over C.
I was wondering,
it's really easy to understand.
Maybe this does not say anything about when you just do it. You put it in the picture over the local fields, maybe you don't gain anything, but it would be interesting to see that, oh, this is really something extremely specific for the infinite places.
Right. I understand your question now. Yeah. So I don't know the answer to your question, but it sounds interesting. Yeah. Yeah. Thanks.
Okay.
There was one thing I wanted to ask.
Yeah.
You started off with Art and Radii duality, and has any of this ever been worked out when you look at Veil-Tal cohomology?
Yeah. So yes, I think. So there's a form of let me make sure that I'm going to tell you the right thing. Right. So the one of the issues that shows up is if you look at the Veil-Tal cohomology. So I'm reminding myself of the story here. So when you do the Veil-Tal thing over like spec of OK, or I guess OF for the purposes of this talk, then I think the issue is that the cohomology looked correct in dimensions 0, 1, 2, and 3. And then it goes nuts in dimensions 4 and higher.
Well, there's all kinds of proposals for what it should be. I mean, it's just... Oh,
well, yeah. I mean, I'm just working from one proposal, I guess, which is the one that shows up in Flach and Morin.
Yeah.
You know, Baptiste Morin just put out a paper maybe 2 weeks ago, maybe 1 week ago, that looks like it's starting to answer some serious questions in this direction. There's some topological cyclic homology showing up in places and stuff, but I haven't read it yet, so I don't know the story.
Oh, okay.
But no, you know, I mean, I would love to know an answer to this. I mean, there's some basic questions that I have about the functioning of the Veil-Tal site that I you know, I have a sense of what I have a sense of some natural looking spaces whose pi1s recover the Galois groups at various places and in the completions and so forth, but I don't have an understanding of the global Veil group on those terms, is what I mean to say.
I just wonder whether your work would be another approach to defining Veil-Tal topology better.
I would really love that. That would make me very, very happy, of course. But I
mean, their constructions get very Baroque. I haven't seen the most recent thing either, but it was getting very, very complicated.
It's tough going for me, at least. I don't know if it's hard for real experts, but but you know, I mean, the obstruction for me is to, you know, I don't have a kind of for lack of a better word, I don't have a Tanakian understanding of the Veil group of a global field.
Right.
In fact, I only know one definition of the Veil group of a global field, which is that you take the fundamental class in X2 and you write down the corresponding extension and you point at it and say that's it.
Right.
This extension of the absolute Galois group by the Edel class group. But I don't know. I mean, I asked Kevin Buzzard, actually. I asked him what the right description of it is, and he seemed to think that was a perfectly good description and that there didn't need to be another one.
Right.
So yeah, I'm mystified. I mean, I think,
I mean, the theory works pretty well over finite fields, right? I mean, I think Veil-Tal topology is very good over finite fields.
Brilliant. Yeah, it has everything you want.
And maybe that case you can say something.
Yeah, so in that case I can say a little something. So yeah, I mean, so in that case there is this category that I can tell you about, which is that let me back up. So if I have something like a quasi-projective variety over FQ, then you can do something like the following. You can go down to gal of FQ. Of course, this is BZ hat. And if you pick an algebraic closure, then you can pick out a BZ here. And if you form this pullback, then this is the V category.
Oh, okay.
Yeah.
That's very natural enough.
And this V category has the property that it's in the same way the Galois category, its representations are constructible sheaves. The representations of the V category are the V sheaves in the sense of Helene, I guess.
Well, is it not so the whole point is that actually the Galois group of FQ has a canonical generator?
That's right. That's right.
And the whole story about
Stop recording, and we can just continue.
Sorry?
I'm going to stop the recording, and we can just